Right. And so yeah, so I'm sorry, I forgot to start the recording. So this didn't record all of it. Um, what I'll do is I'll record this again and I'll upload this. So this will be sort of a video thing. But the other thing you can do is you could make crude drawings of these plots, because today's lesson is all going through and plotting things on paper to plot out functions, and that's what we're going to be doing. And there's just no other way to get around it in terms of of plotting things. And so if you have access to graph paper or you have a printer, you can print out this image of the Cartesian grid and use that. But a lot of people don't have printers. I know it's, keeping a printer functioning in my house is kind of a pain in the neck, because they're expensive and the ink clogs. And so like I say, if we were in class, I'd be handing out uh, photocopies of these Cartesian grids so that you could work on those in class, but it's hard to do that um, electronically. So these are the two options I've come up with, and I'm sorry they're not great. So you can either, and if you come up with something else on your own, great, go for it. I mean, if you want to, and if you wanted to just go on a piece of paper, like in Paint, right? I mean, you could use any one of a number of plotting programs, but you can draw axes, right? Crudely, and then plot points on the axes, something like that. I don't know. I'll leave it to you how you want to approach it, and if you have questions about the best way to do it. Fortunately, there's only this assignment, I think, where it's going to be like that, where you're going to have to actually plot points on a grid. So we'll do it a couple of different ways as we go through the lesson today. And so you can see this example of using this Cartesian grid. Okay, so anyway. So what we're going to work on today is graphing linear equations. And we call them linear equations because they will graph out a line, a straight line, right? And so when you see something like this, where an equation looks like 3x plus 2y equals 6, that's called a linear equation because it will be a straight line. And you can tell a straight linear equation because the exponent on the x and y are both 1, meaning they're just simple power. So for example, this is what I forgot to do. So for example, if I had 2x plus y equals 6, that's going to be a straight line. But if I had something that was 2x squared plus y equals 6, that's not going to be a straight line. That will be curved, right? So this is a curve and this is a straight line. And anything where exponent of x and y are both 1 will be a linear equation, right? So 153, 6.2 x plus y over 5 is equal to 87, right? That's a line. That will be a straight line, right? Because the exponent here is both 1. So we could write this as exponent 1, right? But whenever you have anything else other than 1, it's not a straight line. So for example, if this were x to the 0.5, right, that wouldn't be a straight line. And we could also write, anyway, I don't know if that's confusing or not, but that's why we call them linear equations, because they're straight lines, because they plot as straight lines. And so what we're going to work on today is plotting these equations and what it looks like. And so remember yesterday when we were solving these equations, so if we looked at this equation where we have 3x plus 2y equals 6, right? And we had this table set up. Where is Excel? here. Oops. Here's Excel. Right? And so the equation was 3x plus 2y equals 6. And we would sit and try and find values of x and y that solve that equation. And so, for example, if x is equal to 0, then y has to equal 3. So 0, 3 is the solution to that equation. And then if x is equal to 2, so 2 times 3 is 6, then y has to equal 0, right? So this becomes 2, 0, right? And so you can go through and figure out whether or not points are a solution to this equation. So 4, negative 3. So 4 times 3 is 12, plus 2 times negative 3. So 12 minus 6 is 6. So 6 equals 6. So this will be, right? So you can see these are starting to form points on a straight line, right? Right, that we could connect those into a straight line. And that becomes plotting on a straight line. And they had one other in there that was in the book that was 1 and then 3 over 2. Whoops, 1.5. What? So this point here that I just plotted 1 and 3/2 isn't on the straight line. So that isn't a solution. If we plug in 1 here, that's 3 times 1 is 3, plus 2 times 1.5 is also, why isn't that on that line? What have I done wrong? 1 and 3/2. Help me out here. 1. What have I done wrong? Zero 3 2 0. Oh. 0 3 2 0. Where is 2 0? Why isn't that? Zero, 0, 3. Did this axis get moved? What's going on here? Why isn't this plotting right? Oh, I know what happened. Yeah, sorry. Okay, well, all right. Sorry about that. So what happened was that I had text in here and it was screwing up the alignment of my, never mind. Now it'll work. So now they all work up there. Sorry about that. Sorry, I screwed that up. The having a piece of text here misaligned my rows and columns. And so I need to reset if I'm going to have a label there, but I'll do that later. So anyway, so there you can see that's on a line, but if we choose a point that isn't on the line, say we have 5, 1, right? And we look at that, then it won't solve this equation. 3 times 5 is 15, plus 2 times 1 is 7, is 1. So 15 plus 2 is 17, and that doesn't equal 6, and that doesn't fall on the line, right? So points that don't fall on the line won't be solutions of this linear equation. And by solutions, I mean you plug in values for x and y that make that equation true, okay? Okay. So that's what we mean by graphing a solution. So you recognize the relationship between the solution and its graph. So anything that's on this line that's defined by these points here will be a solution of that equation. And so there are infinitely many points that will satisfy that equation and make it true. Okay. So that's that, and they're all solutions, right? Okay, and so the graph of any equation has a form ax plus by equals c is a straight line. And every point on that line is a solution to that line. And so we can extend this line out to infinity in both directions. And it will, everything on there will be a solution. Okay. And so now they have the graph of y equals 2x minus 3. And so y equals 2x minus 3, right? And one of the things we can do in a spreadsheet is I can sit here and go now, make that a series. Series, column, step value, 5. And then I can say, well, let's let this be plus 2 times 2 minus 3. And I can let the program plot this for me, and this is a straight line, and you'll see it's the same as the one plotted here, right? So all of these points are points I plotted here, but everything in between here on this, that's connecting these points through the center line of those, everything that's in there will still be a solution to this equation, right? So it's a straight line. So you can see that, right? And then you could figure out whether any ordered pair is a solution by whether it's a point on the line. So we could say, well, is 0, 3 a solution? Well, we could look up here and go 0, 3. So 0, 3 won't be a solution, right? We could test point 0, 3. Is that a solution? No. 3, negative 3. 3, negative 3. Is that a solution? No. 2, negative 3. Is that a solution? No. Negative 1, negative 5. Is that a solution? Yes, right? And we could see that because that's up here, negative 1, negative 5. So that's a solution because it's lying right on the line. And so we could pick any point in here and test whether or not it's on the solution. So we could say, well, let's look at minus 6 minus 1.5. I'm sorry, minus 1.5 minus 6.5 negative 6. Is that on the line? Kind of looks like it, right? We don't know for sure. We'd have to put those in and solve that, but right. So probably is close, right? Yeah, and it is. 2 times negative 1.5 is negative 3, minus 3 is negative 6. So y is equal to negative 6. I don't know if that went by too fast, but anyway, so you can, by graphically, just by plotting things, you can tell really easily whether or not something is a solution to an equation. So we can do another example of this. Let's see. So we can graph y equals 3x minus 1, and then we can decide whether points are on a line. Okay. So let's graph 3, -1. And don't worry about this. I'm just fooling around here so I can make this update simply. C3 minus C4. Okay. So there's our line. And this is y equals 3x minus 1 now. And now we can test and see if the points they've given us are on the line. So we can have 0, -1, right? Does that lie on the line? No. So that's not a solution to this equation. Let's look at 2, 2, not on the line. 3, -1, not on the line. -1, -4, -1, -4, not on the line, right? So it's really easy, and if we wanted to get really clever about this, what we would do is we would modify our spreadsheet so that it, let's see, so edit 12, 12. So we can have these be a different color so we can see them. Whoops, what did I do? Damn. All right, we'll try that again. So let's try and do this correctly without blowing things away here. 2, 12, 12. This is line. Okay. Add test. Okay. Okay. If I click on that, format data series. Okay. Marker. Options. And so we'll make them blue, and with the line, we'll make that. So now you can see really clearly which ones are the test points and which are not the test points. And we can also, to make it a little bit easier, we can add a whoops linear. There we go. So there we've added the line. So you can see clearly things that are lying on that line are solutions, things that are lying off the line are not. And you could do this with any point. So you could have 4 and then say 9. Oh, oops, that's out of the range. 4, 9. Right. So you can do that with any point and see if it's going to be a solution or not by plotting it, by plotting the line and then seeing if the point is on the line. And then we can also graph a linear equation by plotting points. And so and we call this a point plotting line. So let's graph the equation y equals 2x1 by plotting points, right? So we'll go down here and I'm going to clear this off. So we can do it this way. And maybe we'll go back to the other way with paint, just so we can do an example. Okay, So here we're going to graph an equation by plotting points. And so the equation we're looking at is y equals 2x plus 1. And so let me pull that up on here. So we're going to write that as y equals 2x plus 1, right? This is going to be awesome. Okay. So for each, so the way you do that is you just pick values of x and then solve this equation. And it doesn't matter which values of x you pick. You can pick them to be convenient. You can just pick whatever. So the example they use in the book is they say, well, let's start out with x equals -2, right? And so you would substitute that in. So you'd say 2, I'm sorry, this is y equals, so y is equal to 2 times -2 plus 1, right? Which is equal to -4 plus 1, which is equal to -3, right? So that's what they've done there. They just substituted that in, and you come out and you get -2, -3. And so then you would plot that point for x is equal to -2 and y is equal to -3. So 2, -2, and then -2, and then -3. 1, 2, 3, right? So then you just click on that, and I'm just using a marker pen and then a big thickness, so I've got a point there. It doesn't have to be really accurate here. It can be sort of, I mean, the cursor slips around and everything. So let's look at the next one. So we've got x equals 0 here, right? So we substitute in 0. So y equals 2 times 0 plus 1. So y equals 0 plus 1. So y equals 1. So when x equals 0, here, y equals 1. So we can put a point there, right? And then the next point they plot is x equals 1, right? So 2 times 1 is 2. 2 plus 1 is 3. So y equals 3. So for x equals 1, y equals 3, right? And you could see the line forming here, right? So you could see this straight line. So now we've plotted that line, and you could say, okay, well, what if we take x equals -1? So that would be 2 times -1 is -2, plus 1 is -1. So at -1, x equals -1, y equals -1. We plot a point there, and we can see it falls right along that line, right? So that's how you do this by plotting points. And where's the next example? Right, so they made a table, and then they went through and they plotted these points, and they come up with this straight line. And typically, if you're working on a pen and paper, then what you'd use is use a ruler to connect those lines and draw it on there with a ruler. With this, you could probably use they probably have a tool in here to make a line, but I'm not going to bother to do that. But you could start here and extend the line like that, right? And of course, if you're working in the spreadsheet, it'll sort of draw the line for you automatically if you're doing that. Okay. Okay. So one thing that is always true is that 2 points will always determine a line, right? So if we were confident in our skills, we could have started with any of these 2 points and drawn the line, right? You could plot that point and draw the line between the two of them. But if you calculate 3 points, that kind of gives you an idea whether or not you've made a mistake. Because if you have 3 points, they don't necessarily have to be on the line. So if you've made a arithmetic calculation, you've made a mistake somewhere, you didn't do your arithmetic correctly, you misplaced a number or something like that, it'll show up because, right, you'll have a point that's like here, right? And now you've got the question is, well, is this the correct line? Is this the correct line? Or is that the correct line? and you don't know, so you can go back and you can check your arithmetic and see which one of these points is wrong. So when you're plotting a line, it's always a good idea to use 2 points. I mean 3 points, because you can tell if you've got a mistake, right? Because you would know if this one is lining up along the line, I forget where that was. Was it there? 2, 1, 2, 3, 4, 5, 1, 2, 1, 2, 3, 4, 5. Yeah, there. Right. So lining up like that, you will find that it's easy to see which your mistake would be, right? So now we can do another one, okay? So we'll go over here, whoops. So they got y equals negative 3x, right? So let's look at x equals 0. So for x equals 0, y equals negative 3 times 0, so y equals 0. So that means that the point is there, right? And now if you have a linear equation where it's just y equals some power of something times x, you know that the line goes through the origin. It goes through 0, 0. So that will always give you one of the points. If your equation, your linear equation looks like this, it goes through the origin, right? So now we look at x equals 1. Well, y equals negative 3 times 1, so y is equal to negative, oh, they've got a typo here in the book. Y is equal to negative 3. This should be a negative 3 here in the book. It says 3, but it actually means negative 3, right? So y, when x is equal to 1, y is equal to negative 3, right? And now we look at, they've got negative 2. We're going to do negative 1. So when x is equal to negative 1, this is 3 times negative 3 times negative 1 is positive 3, so y is equal to 3. Right? And then they've got negative 2 and positive 6, right? Because it's the same thing. So there's our straight line going like this. And if we go down in the book, we'll come out and see they get the same thing. All right. So it's relatively straightforward on how to apply these, and I'm hoping it's not too confusing how you work between x and y values. And really the key here is being able to solve these linear equations sort of in your head. And so let's look at plotting this graph here, y equals x. And so if we go over here, right? So when y equals x, what that means is we pick any of x value and we would plot the same y value. So pick an x value, say 3, that means y equals 3, right? Negative 4, right? Well, that means y equals negative 4. What about 2? Well, x equals 2, then y equals 2. Negative 1, x equals negative 1, y equals negative 1. So y equals x is just a line that bisects the Cartesian grid on a 45-degree angle. And if it's a negative x equals y, then that line would do this. It would come down through here like that. It would be the other direction, right? Okay, so this is x equals negative y, and this is y equals x equals y, or x equals y. Okay. All right, so let's graph the equation as one more example. Y equals 1/2 plus 3. So again, we're picking 0, so x equals 0, and it's always easy to start out with x equals 0, right? It's just a really easy one to do. So when x equals 0, plug that in, you get y equals 3. So 0, 3. So x equals 0, y equals 3. Right? Then they pick x equals 2. Well, when x equals 2, 2 times 1/2 is 1. 1 plus 3 is 4, so y equals 4. X equals 2, y equals 4. Okay. X equals 4, right? So x equals 4, 4 times a half is 2, plus 3 is 5. So x equals 4, y equals 5, right? So there's your straight line doing this, right? Now suppose you took x equals -2, and you said, okay, well, x equals -2. -2 times a half is -1 plus 3. But suppose you forgot and you said, oh, well, I'm going to make that instead of -1 plus 3, I'll get 2. I added 1 and I got 4. So you said -2 and 4, and you plotted that here. You go, wait a minute, whoops, that's not on the line, so that can't be right. And you go back and check your arithmetic, and you would calculate and put it there, and you get it right. So that's how you can use plotting as a check on your arithmetic if you're working with linear equations, and why if you plot more points, you can figure out if something, excuse me, is right or wrong, okay, or if you've made a mistake, arithmetic mistake. Okay, and so there's the line that we just plotted, and it's looking right there. Okay. So there shouldn't be anything particularly mystifying or this isn't a deep or heavy concept, I think, in terms of what's being asked in doing this. You pick a value of x, and then you calculate this equation to find the value of y. And if anything that is confusing there, it's this idea of free choice, that you can pick any x you want to, right? And if you had a huge sheet of graph paper, you could put x equals 1,000,000 in here just for the hell of it, and try and plot, you know, 1/3 times 1,000,000 minus 1, and then figure out what that would be, right? If you wanted to. Okay, so now what about an equation in this form? These other equations, they've been y equals something times x plus or minus something, right? So we just had to plug in x and then just do this sort of arithmetic. But what if we've got something that looks like this, x plus y equals 5? Well, that's not quite as easy to work with. At least it looks a little more daunting, right? Because all of a sudden now you've got x plus y equals 5, right? Well, you could do the same thing. You could just substitute in values of x, or the other way you could do it is you recognize that I can put x on one side of the equation and y on the other if I subtract x off both sides of the equation. So if I have x plus y minus x equals 5 minus x, right? I can subtract the same thing off both sides of the equation. That gets rid of x over there, and I can rewrite this as y equals 5 minus x, okay? And then I can just solve this the exact same way, or plot this the exact same way I was doing this before. The other way to do it is the way they've done it here, is they've said, okay, pick a value for x. So let's say x is equal to 2. So we'd have x equals 2, 2 plus y equals 5. And then they would subtract 2 from both sides so that y is equal to 5 minus 2, which is equal to 3, right? It doesn't matter which way you do it. If it's easier for you to rearrange the equation so it's in this form, go ahead and do that. If it's easier for you to work in the equation this way, it doesn't really matter. If you get more familiarity with doing this, one way is as good as another, really. And you can almost do these in your head by doing the arithmetic in your head, the mental math, as they call it, right? So what they've done with this one, we'll go back to start plotting these, right? So they put in x equals 0 again, so x equals 0, and they come out with y equals 5. So when x equals 0, y equals 5, right? And then they put x equals 1, and they get 1 plus y equals 5, and so then they subtract 1 from both sides, and they find that y equals 4. So when x equals 1, y equals 4. Okay. And then they looked at x equals 4. So they had 4 plus y equals 5. So they subtract 4 from both sides and get y equals 1. right? And again, you can see the straight line formula that goes right through here, right? Right, and there's the answer, the same answer they got. All right. As I said, in the previous example, the 3 points we found were easy to graph, but this is not always the case. Well, let's see what happens when we have 2x plus y equals 3. If y is equal to 0, what is the value of x? Well, here they did it in reverse. They picked the value of y, and then they want to find the value of x. And so what they did is they have the equation 2x plus y equals 5, right? And they said, well, let's solve that for y equals 0. I'm sorry, equals 3, right? Right? And so for y equals 0, this equation becomes 2x plus 0 equals 3, or 2x equals 3, or x equals 3/2, right? Which is equal to 1.5, right? X is equal to 3/2. So if the equation is more complicated, what happens is that you're going to be solving this sort of equation for the whole time. Now, the other way you could do this is the way I just pointed out, is we could say, well, let's rearrange this equation so we get 2x plus y minus 2x equals 3 minus 2x, right? And so that we would get y is equal to 3 minus 2x. And then we could just substitute in values of x and y like we have before, right? Right. So for example, if, did I do this right? 2x plus y equals 3. Yeah. No. Right. Okay. Yeah, they've just got it written wrong here in the book. Okay. So we could build up our own table here. I think this table here in the book is wrong. So for x equals 0, y doesn't equal 5, x is equal to 3. So this, ignore this table. This is a bad table. They've done a bad job here. So we'll recreate this table over here. That's pretty funny. Right. So we could go through and solve this equation each time for x and y. So when when y is equal to 0, so for y equals 0, we found up above, then x is equal to 3/2, right? And then let's try for x equals 0, right? And we could substitute in here when x is equal to 0, y is equal to 3, right? And then we could try another point that they've done here. X is equal to -1, right? So for x equals -1, 2 times -1 is +2, so y is equal to 5. So x equals -1, then y is equal to 5, right? And we could see if we did a good job by coming over here and plotting these points. Whoops. So when y is equal to 0, x is equal to 3/2. So that point is there, 3/2, 0. When y is equal to 3, x is equal to 0. When x is equal to -1, y is equal to 5. Oh, that's because I've drawn that point out of line. I think that's right. That seems pretty linear to me. Okay. So again, these aren't the points that are plotted in the book or are given in the book. I think they've screwed up their arithmetic here, right? So Oh, and here they showed the same method I just did, where they rearranged the equation to give us y equals negative 2x plus 3, which is the same as 3 minus 2x, right? So they did the same thing, and the solutions for x equals 1, x equals 0, 1, and negative 1 are shown. This isn't right. When x equals 0, this should be 3, so this should be 0, 3. When x equals 1, this should be 1. Negative 2 times 1 is negative 2 plus 3 is 1. And when x is equal to negative 1, this should be 5. So this table here is screwy. Somehow they didn't do it right. But you can see that they get the same answers we did, right? Although they plotted 1, 1 instead of negative 1, 5, right? If we put 1, 1 on here, whoops, it's going to be on the same line. Okay. All right. So let's do the equation 3x plus y equals negative 1. Whoops. Okay, so 3x plus y equals negative 1. And they rearranged it as we've shown up above. So they get y is equal to negative 3x plus 1. And so for x equals 0, you come out with negative 1. So 0, negative 1. So x equals 0, y is equal to negative 1. And now for 1, they substitute 1 in here. They got negative 3 times 1 is negative 3, minus 1 is negative 4. So 1, negative 4. So 1, negative 4. And then negative 1. So negative 1 times negative 3 is positive 3. Positive 3 minus 1 is 2. So negative 1, 2. Negative 1, 2. And again, you can see the straight line there, which is really what they've got right there. Okay? So what are the forms for horizontal and vertical lines, right? So if a line is horizontal, what does that mean? Right? So if a line is horizontal, what does that mean? It means for any x, y is equal to the same number, right? So it doesn't matter whether x is equal to 1, say like if y is equal to 3, right? It doesn't matter whether x is equal to 1, x is equal to 4, x is equal to negative 5, it's always equal to 3. So what would be the equation for that line? That equation would have the form y equals 3, right? Because y is equal to 3 for any value of x, right? So any horizontal line is going to be equal to, it's going to have the form y is equal to a, where a is any constant. Anything from minus infinity to plus infinity will have the form y is equal to a, right? Well, what about when x is equal to a? What does that look like, right? Okay, so suppose x is equal to 2, right? What does that look like? That means for any value of y along this line, x is going to equal 2, right? So a vertical line has the form x is equal to 2. Horizontal lines, we'll have x is equal to a. So that's a vertical. And then y equals a, that's, horizontal. Okay. And so the book will go through and give you examples of vertical lines that are all x equals negative 3 for any value of y, right? X equals 2. And then the same thing for y. Y is equal constant, okay? All right, let's see. What's the next part? Okay, so it should be relatively clear what the difference is between a line that has the form, say, of y equals 4 and a line that has the form of, what did they use? Y equals 4 times x, right? Okay. And so let's look at what that would look like, right? And so what have they got? Yeah, they've got these equations. Good. Okay. So this is y equals 4x, and they've given us some points here to plot. And so we could plot 0, 0. And then we've got 1, 4. And we can't plot the other one because our scale doesn't go up, but we can make our own. So we'll just try -1. So if we have x is equal to -1, 4 times -1 is -4. So y is equal to -4. -4. There. Okay. And now where's the line here? We'll put this in a different color just to be clever. And we'll put the line in here, y equals 4. Where is that? Well, that goes along for all values of x. So there's y equals 4 along here, right? So there's that line. So you got the horizontal line and the linear function, and you can see they cross at this point 1, 4, right? So that we call that the intersection point, and that will have excuse me, relevance if you go on and go on to take the algebra sequence, where we'll use this as a method for solving equations, for solving algebraic equations. Okay. So again, I'm not going to draw this and belabor this in the book, but here's the example in the book where they draw y equals -3x and y equals -3 in the same coordinate system. So you can see that there's y equals -3x and there's y equals 3. Okay. So now we're to the exercises, and as I assign, as usual, 10 problems to this set, and they're listed in um, on Canvas. And so I'll go through and do a couple of representative examples. So assignments. And maybe what I'll do as part of this is I'll go through how you would set up Paint to do plotting on a grid. And so it'll be on this lecture, and you can fast forward when the video comes up to reference back to it. Okay. So the lesson is here. And so again, I've got the table for you to find where you are in the book. And so I've assigned 40, 43, 46, 49, 52, 55, 58, 61, 71, and 106. So 40 is just, it doesn't require plotting, so I'm not going to bother with that one, but it asks you to determine whether an ordered pair is a solution to the equation. So the first one is 0, -4, right? So we would do this just the way we did them before. You plug in x equals 0 here, so you get 0 minus 4. Does that equal -4? Yeah, because -4 equals -4, right? So you would just do that for the other three problems, okay? But now let's look at, what was the next one, 45? 43. 43, which is graphing y equals 3x minus 1 by plotting points, okay? So let's go and do that in the spreadsheet just for the heck of it. All right. So we'll go down here. And the function that we're going to graph, oh wow, look at that, y equals 3x minus 1. Okay, so we can just do it up here. Okay, so y equals 3x minus 1. So, oh, Cartesian must have dropped off because his computer crashed. Okay, so let's pick 0. Oh, dang. And so we'll just calculate this as plus A2 times 4 plus C4 so 0 is minus 1. Okay. Now let's pick another value. Let's say minus 2. So there it is, going to -7. And then let's pick 1. There's 2, right? So you could see things are lining up along the straight line. You could pick 3. There's 3, 4, right? So that would be that function plotted as a straight line. Okay. So I think I assigned 46 next. 46. So let's jump over to 49. So y equals minus x minus 3, right? So y equals minus x minus 3, right? So y equals minus x minus 3. Ah, come on. Minus x minus 3. Perfect. Minus 1, minus 3. Oh, huh. It did already for us. All right. So let's plot some points. So again, start off with 0. X equals 0. Y equals -3, right? Let's try 1. Y equals -4. What about 3? Y equals -6. What about minus 3? There. Okay. So it shouldn't be, the assignment will take time just because it takes time to plot things. And so let's go through, and I don't know if people want to use a spreadsheet or they want to use Canvas. I mean the Paint.
If I go and buy some graph paper,
Yeah,
can I
if you
just
want to buy graph paper, go for it.
and then just plot it and send you a picture of it?
Yep, exactly. Perfect. That's the
Okay,
perfect thing. And you can actually, if you don't want to go buy graph paper, you can take a piece of regular line notebook paper and
and just make my
draw some vertical lines on it. Right. That's perfectly acceptable.
Okay.
Right. So that's perfectly acceptable. So it seems like this is probably enough of guidance. I think this is a relatively straightforward assignment, so I don't think it'll be particularly. There isn't a particularly. It's not a.
Yeah.
It's not a deep heavy concept, right? So it's pretty applied and focused. So I think you shouldn't have too much trouble with it. So maybe I could stop there, unless people want to go through more examples. But a lot of these examples are just what we've been doing all class period. We've been plotting these sort of these simple functions, right? Basically just a bunch of plotting by points, plotting points. I don't think I assigned the word problem at the end. 106. Okay, so I assigned 106. Oh, 106 is another one. Just graphing equations. So I don't think there's anything in here that is different from what we've gone over. There aren't a lot of word problems from this. The word problems in graphing these equations will come in the next section, I think. Right? when we start to use these to solve for different parts of the graph. We talk about slope and intercept. Okay. So I'm going to stop for today. If anybody has any questions, they can ask now or ask in chat. And
Okay.
and Santos, maybe we can, maybe you could stick around and we'll go through and I can do your waivers form for you. I could fill it out and then get it
Yeah,
submitted.
that's fine.
Okay. So Logan, unless you have questions, you could sign off because I don't need you to do the waivers thing. What if he's gone? What if he's here? All right. So are you going to be around for a couple of minutes, Santos?
Huh?
Are you going to be around for a couple of minutes? Because what I'll do is I'm going to set up a separate Zoom chat, and then we could do that separately, right?
Yeah, if you want to just email me the link real quick.
Yeah. Okay. So I'll do that in just a second. But I'm gonna shut down my screen share, and I'm gonna shut down this, and I'll give you the new meeting in just a minute. Okay.
Yeah, that's fine.
Okay. Cool. So talk to you in just a second.